Mhm. Good evening, everyone. Can you please confirm if I'm audible?
Good evening, sir.
Yeah, I'm audible, right? Clearly?
Yes, sir. It's clear.
Okay, yeah. So let's start with today's live session for week 8 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, a PhD student from IIT Jodhpur. And in this week, I'll be assisting in solving similar assignment problems that has been given to you in the week 8 assignments. That will help you in solving the assignments more quickly, and it will give you more insights and more concepts about the topics that we have for this particular week. So this is a course outline. We have already covered the content till week 7, and as I already told that from week 7 we have started the most important device for this course. So we did read some concept about the MOS capacitor, like how does it work, how does it look, why, how do we make the band diagram for a MOS capacitor. Then apart from that, we read about several things such as accumulation region, depletion region, and inversion region, etc. when it occurs in a MOS capacitor. And we also like gave some, I guess, give it a go to some numerical problems that were related to our ideal MOS capacitor, in which we were solving about what region it is in, what type of MOS capacitor it is, etc. So in this particular week, what we'll be doing is we'll be covering some more concept that will end the MOS capacitor for this particular course. And in this week, we'll be covering what is a threshold voltage. Like in a brief, we have already seen what is a threshold voltage for a MOS device, but we'll be going more into the depth, like how it comes and what is the value of that. Like we'll be deriving some formulas, or like I'll be giving maybe some formulas, and we'll be doing some of the numerical problems related to that. Then we'll be seeing the CV measurement. We did discuss the CV plot, how it comes, like the U-shaped plot for the CV curve. And now what we'll be doing, we'll be doing it for high frequency and low frequency CV analysis for a MOS capacitor. Like what does basically changes in the CV characteristics if we have a high frequency or if we have a low frequency. So till now, whatever we were doing it was for an ideal case. Ideal case means we were doing it for a low frequency case, in which in which the carriers has enough time to what to say, to maybe capture the change in the voltage. And the For this week, we'll be also covering some of the high frequency CV measurements, how the plot looks, something like that. And we'll be looking some of the non-idealities, such as work function of flat band voltage. We already know what it is, but some more things are, if we can use some high K dielectrics, etc., or not. So yeah, this is the particular week concept. And in this week, we'll be closing out for the MOSFET, and the next week is the most important, because then we will be starting for the MOS transistor, that is a MOS, a field effect transistor. So if you know MOSFET, basically it is the same as MOSFET. So let's start this particular week session without any further wait. So let me give you a very brief, like very quickly, what did we did in the last lecture. So the main thing that we read about is we are applying a certain gate voltage, and we did take three different cases for the understanding. So let's say if I have, maybe I can make three quickly. Yeah, so let's say I have this metal, and this is grounded for all the cases. And let's say I have this SiO2. So this is nothing but basically a MOSFET, because it has a metal on top, it has a semiconductor uh, or sorry, a insulator in between, that is oxide, and then we have a semiconductor, which is, let's say, a p type substrate, for example. So p type substrate, we all know now that it is a NMOS. So we what we did is we took three cases. One was, so we applied VG in all the MOS caps, let's say. So this is what we did. So was the first case was when we applied VG, which was even less than the flat band voltage. That is, it was negative for the first case. So by negative, what I mean is we have some negative uh, electrons or ions at the interface. So can anyone tell what was this particular case? I hope you remember this. This was all basic.
Accumulation.
Yeah. So what happens when once we apply a negative voltage? What we have is we have the majority carriers as holes in the p type substrate. So what happens is the holes accumulate near the SiO2 and semiconductor interface. So basically we have certain negative charge and we have certain positive charge and we have an insulator inside in between. So what we were claiming it as, it was nothing but the oxide capacitance. So for this particular case we had a COX, and for this particular case what I can say is, for this particular case maybe I can draw a line here, we had accumulation. What was accumulating? Accumulation of majority carriers, that are holes in this case, near the SiO2 and Si interface. Then what we did is, the second case was when we applied the voltage which was greater than, let's say, VFB, but it was less than the threshold voltage, or the value we were terming it as when the inversion was happening. So this was the second case. So in this particular case we applied a positive voltage. That means we had certain positive charge around this metal. And what was happening because of this positive charge? The minority carriers now. So minority carriers are the electrons. Oh, sorry. Minority carriers, yes, are the electrons, and we have this in the form of, let's say, Na minus for a p-type substrate. So we had certain depletion region that was getting created. Let's say this XD is the width of this depletion region, and we had certain Na minus ions which was there. So what was happening is, now this is our depletion case. So in this, what was happening is depletion region was getting created, and basically the acceptor ions are getting exposed at the surface. And the third case we took was again VG, which was positive, but it was even greater than the threshold voltage. That is what I'm naming as VT. So in this, what was happening is not even the Na minus, but the minority carriers, which are electrons. So maybe I can denote it with filled circles now, because I denoted holes with empty one. So what was happening? These electrons are now getting in picture at the SiO2 and Si interface. So basically we had a positive voltage and we had a pseudo metal gate now. So let's say this is positive and this is basically a negative charge of carriers, and this is what we were naming as inversion region, because we started with a negative and a positive uh, charge, and we have inverted it, and we have gone from positive to negative. So that is why we name it as inversion region. And we also saw in the band diagrams that the Fermi level is crossing, or the Fermi level is basically, I hope you remember this was something like this. So this was EF, and it was basically here, it was crossing this uh, EI. So this EF was going above that EI, and this EI was below. So this was the P type substrate, and we were getting an N type substrate at the interface. So we were basically inverting the uh, nature of the semiconductor. So that is why we were also calling it as inversion region. So this was the very basic that we already covered in the last lecture, and in this week's we'll be covering The first concept, that is what is this threshold voltage. So I am naming this as Vt in all the cases you can see. So what is this threshold voltage and how do we calculate this? So I guess we know that what is threshold voltage as of now. It is a voltage at which I guess we did discuss that at which the surface potential becomes the twice of Fermi potential. We were getting the inversion, and this particular voltage is nothing but the threshold voltage at which this happens. And we saw in the CV plots also. Maybe I can make a quick plot. It was something like that, and this particular voltage, the threshold voltage. Sorry, should make it here. So this is C V. So now we'll be discussing about how do we calculate this threshold voltage. So this calculation of Vt. So we already know that this threshold voltage is achieved during the inversion region when the surface potential become at least twice of the Fermi potential. So what will be the step one? First of all, I will go one by one. So we'll first achieve the flat band voltage. So we'll apply the increase of voltages in steps so that we get to know that what is the final expression for the threshold voltage. So the step one will be, first we should be achieving the flat band voltage, and then we'll go towards more and more positive voltage. So once we increase, so let's say we keep on increasing the gate voltage. I'm denoting the gate voltage with Vg till this flat band is achieved. So what I mean here is this Vg should be at least equals to the flat band voltage, and flat band voltage we all know, we discussed it. It is nothing but equals to phi ms for a flat band case, and I am also taking the non-ideal charges that are trapped, which is I am denoting as QSS. Do you have any problem in understanding this? Like, this is the expression till we have achieved the flat band voltage, and flat band voltage was equals to the Fermi, sorry, not Fermi, the metal semiconductor work function. Because of the flat band, they will have the same uh, level. So for an ideal case, this phi ms will be going to be 0. But once we have some non-ideal cases, this will have certain positive or a negative value. And this QSS is nothing but the trapped charges in the oxide. So it will also make a drop. So basically we know that Q is equals to CV. So from that I have written this voltage as Q by C. The drop that will come due to the trap charges, if there is any. Is there any doubt in this particular thing?
Sir, why are we doing minus QSS by Cox?
Yeah, because of the negative charges. That is not a problem. There will be a voltage drop, like the voltage will decrease. So maybe here you can see if I have certain charges, maybe some negative charges. So this ideal case should be that if there are no charges, this particular voltage is, let's say, V. But if we have some charges, there will be a voltage drop due to this particular thing. So that will be V minus V naught. So that is what I'm doing similar here. These charges are negatively charged.
Can't we have positive trap charges?
Yeah, we can have. So that will depend upon the sign. So if I write the mod of QSS here, then it will be positive.
Okay, okay.
Yeah. So since in general we have negative charges in all the numerical, so the intention is not to get not to confuse you guys. So that is why I'm writing the in general formula. So now the step two we have already achieved. Let's say a flat band. Now what we'll do is we'll deplete the semiconductor oxide interface. So for that, what we'll have, the gate voltage should be at least equals to the VFB, and plus I'm writing now this charge as Q depletion over Cox. So now I'll write the mod, that will be better. So now what is this Q depletion? I hope you know that this is nothing but the charge. So do you know this formula, that it is nothing but Q into Na into Xg? Are you aware of this? Because This is nothing but the charge density, so it will be the acceptor ion concentration multiplied by the width of the depletion region. Yes, this is simple. Does it make sense? Is there any doubt in this?
Clear, sir.
Yeah. So let's say we have depleted the surface for which we are getting this Q depletion by Cox. Yeah. And I hope you know that this both the things are coming now inside this VFB. So maybe I can highlight this. So this is VFB and this will come here. So once we will go to the inversion, this both the things will get added and some inversion charge that is required will also get added. So right now we are in the depletion part, so I'm discussing that. Yeah. So we have this Q depletion. So let's find out a certain relation for Q depletion. So what happens? Maybe we can calculate the depletion width. That is the most asked numerical in the assignment problems. I'm denoting it with XD for now, X and subscript D. So we did the derivation of PN junction diode. I hope you remember. So in that, what we apply is we apply the Poisson's equation. Sorry, can anyone tell what is Poisson's equation? Any idea? Let me give you a hint. Maybe.
Minus rho v by epsilon.
Yeah, so it will be minus rho v by epsilon, or if I write it in terms of electric field, then it will be rho v by epsilon. So we did calculated the charge, electric field, and potential profile using the Poisson equation. So we'll be doing the same here to calculate the depletion width. Also, one more thing. Right now, I want to ask that can anyone tell maximum depletion width is achieved when we have a surface potential? How much? Can anyone tell? I'm asking with respect to the Fermi potential. The maximum depletion should be there just before the inversion, and inversion happens when this surface potential becomes what? Any guesses?
2 5 F.
Yeah, 2 pi. So the intention of calculating the depletion width of all this derivation is to calculate the maximum depletion width basically, because the question in general asks about the minimum capacitance or the maximum depletion width. So they are the same thing. So if we have the maximum depletion width, we can calculate the minimum capacitance. So yeah. So I'm calculating the electric field the similar way we did in the diode part. So we know that the charge density is nothing but minus QNA, and electric field will be simple now, minus QNA by epsilon S. So I am doing it a bit quicker. If you have any doubt in between, you can ask. This is very simple because QNA x by epsilon S and plus let's say some constant. This is what the case for a diode also. We calculated it at the same thing and then we applied the boundary condition. So let's say at x equals to xd, we know that the electric field will be 0. Same case for diode, and we from this we can calculate the constant QNA xd by epsilon S plus C, and the electric field will come out exactly the same, which is minus QNA by epsilon S x minus xd, which was the case for the n side. Now what we have is we have sorry, yeah, electric field is nothing but minus dV by dx. We all know. So again doing the same thing. So the voltage will come the integration of minus d e dx, and we already have the value for what to say, not energy, the electric field. So it is minus was already there. So I'm writing QNA by epsilon S x minus xt dx, which will give me a potential. Maybe I can denote the potential by phi because we are doing it phi s phi f from in between. So this V is nothing but phi x only. So this is QNA by epsilon. This is x square by 2 the integration, and this is will be xd times x plus C. Let's say this is I'm writing as C2. So now applying the boundary condition again. So let's say we have since we have a bulk p-type semiconductor, so let's say it is at zero potential at x equals to xd basically. So at x equals to xd, we have not applied, not v, phi is 0. So 0 will be qna by epsilon s xd square by 2 minus xd square plus c2. So what it will give me, I'm writing the phi f, sorry, psi x directly now. We already had this term which is x, sorry, x square by 2 minus xd into x, and this will boil down to half. So this will be qna by epsilon 2, and this is xd square. So this is the potential profile. Again, it will come similar to that of what I was saying, the diode. Yeah. So now we'll calculate with respect to surface potential. So what we have, the surface potential, I'm writing psi s is nothing but the potential at x equals to 0. That is at the interface when we don't. Uh, so surface potential is at the interface. So I'm putting x equals to 0 for this case, for which I'll get, I guess, only this part because this and this will get 0. So I'll have the surface potential as q n a x d square by 2 epsilon s. And from this, we'll be calculating basically xd square will be now 2 epsilon s phi s by q n a. And this xd is, sorry, nothing but 2 epsilon s phi s by q n a. So this is the depletion width, and if I want to calculate the maximum depletion width, so what we'll do is we'll take this phi s as 2 phi f, and it will be nothing but, I'm writing 4 because of 2, and then we will have Fermi potential by qna, and the Fermi potential we know it is nothing but vt ln na by ni. Is there any doubt in this? This is simple, I guess. Any doubts?
No, sir.
Okay. So we can also calculate the depletion charge. I hope you remember we wrote qnaxd. So we have qna already, and xd we have just calculated, which is this. So it is 2 epsilon s phi s by qna. Qna will come in under root. So 2 qna epsilon s phi s. This is the depletion charge. If someone asks what is the depletion charge, this formula will give it out. So now what we have reached is, I hope you remember that we were doing this, that the gate voltage is applied till we depleted the carrier. So the gate voltage right now is VFB plus under root 2q epsilon s phi s na by Cox. Yeah. So step 3 is further apply the gate voltage such that we get an inversion layer. So to get the inversion layer, the voltage that we require is addition of 2 phi f only. So what we have is, so we have made the surface potential equals to 2 phi f. So we need to add the same. So we have this VFB, we have this Q depletion by Cox, and we have the surface potential that is required to get the inversion. So what we can write is this is as 2 phi f. Sorry. So now this particular gate voltage, once it is applied, we are getting into the inversion. So this particular gate voltage is nothing but, what do we call this gate voltage now?
threshold voltage.
Yeah. So this is how we calculate threshold voltage region by region, and we get to know how this threshold voltage comes. So we have a final relation. It is nothing but VFP plus Q depletion by C of plus 2 pi F. And you can write Q depletion in terms of that we have just derived, sum under root and other things. So is it clear? The whole depletion width and all. And the band diagram, I hope it was clear earlier also.
Sir, I have a doubt in first slide
First slide. Um,
where you compared all three modes.
okay, okay, yeah, sure. Yes,
Here, in the case of accumulation, we
yes,
have only oxide capacitance, right?
yes.
My doubt is, can we consider yet another capacitance like formed by the base metal and the holes that have accumulated with silicon as the dielectric?
Okay, yeah, I get it. So you're asking maybe this capacitance.
Yes.
So yeah, in general, in any case, we don't consider it because of this. So in practically, what I'm trying to say is this width in which the holes is getting accumulated is 1 nanometer. So we are acting it as a metal layer, and this particular substrate in practical is, let's say, maybe 500 nanometer. So due to a very extreme width, what we'll have is the capacitance is nothing but epsilon A by xd. So if this is very large, this capacitance will have a very less effect on the results also. So that is why in general we don't even consider it for any case.
Okay, sir. So whatever is happening is only at the interface.
Yeah. So in the
Okay.
band diagrams also, maybe if you remember, I have, I guess. Yeah. So these band diagrams, whenever we see, we only care about this interface only. Like we don't even see what is happening here. We are not we are not caring about this.
Okay, sir.
Yeah. Okay, so shall we proceed?
Yes,
Maybe,
sir.
yeah. So I guess this is already done in the last lecture, right? These questions, these two.
Yes,
If
sir. We
not,
solved them.
yeah, yeah, fine then. So maybe I can give you a question based upon the derivation that we have just did. So let's say we have a MOS capacitor. So can anyone tell, are you in the WhatsApp group? Whosoever has joined.
Yes, sir.
So can you share the link? I guess someone is asking for the link in that group.
Okay, sir. I'm sharing.
Yeah, just do it. Till then, I'm writing the question. So let's say we have a MOS capacitor. Uh, okay, give me a moment. Maybe I'll see for a easier problem. Okay, just we'll go with it. So we have a MOS capacitor which is given, and we have HFO2 as a gate dielectric. So HFO2 has epsilon, relative epsilon of 25, I guess, and we have a P-type substrate. So let's say the electron affinity for the substrate is given as 4 electron volts. EG I'm giving as 1.5 electron volts. The For oxide, the relative dielectric constant is 10, and Ni I'm giving as 10 raised to power 12. Please consider all the values that I'm giving because that are meant to be for the simplification of the numerical or the calculation. Na I'm giving as 10 raised to power 18 per centimeter cube. Now the gate is made up of some metal whose work function is given by, let's say, 5 electron volts, and the gate oxide thickness is 100 angstrom. So let's say Tox is 100 angstrom, and it has some fixed charges also, which is 5 into 10 raised by 10 uh, q coulomb per centimeter square, and where this q is 1.6 into 10 raised by minus 19. So you need to calculate, the first part is a VFB, the second part is a XD, and the third part is a threshold voltage. So this is what we did just now, the exact derivation step by step. So what you need to do now is the calculation part. So I hope you do want to try this question, right? Or shall I do it by myself?
We'll try, sir.
Okay, yeah. So maybe you can take 2-3 minutes and let me know even the answer for the first part, and then we'll move ahead quickly. Uh, so one clarification that the oxide relative permittivity is 25 because I've given HFO2, not SiO2. And the silicon relative permittivity is 10. That is in general 11.7, but for the simplification I've given it 10. So can anybody tell how can we do the first part? Like what are you following or something like that?
Flat band voltage would be
Mm.
5M plus the trap charge by capacitance.
Yeah, not 5M but 5ms, right?
Yes, sir.
The trap charges by the oxide capacitance. So this is the first part. So first what we need to do is we need to calculate the 5ms, which is nothing but 5m minus 5s. And if you remember 5m, how to calculate 5s, maybe I can make a band diagram. So let's say this is EI, we have EFP because of the p types of it. So this is the electron affinity till conduction band. This is Eg by 2, and this is EF minus EI. Oh, sorry, EI minus EF. And this whole thing is basically phi s. So maybe I can also solve side by side, and if you get the answer, you can type in the chat box or you can open your mic and let me know what is the flat band voltage that you are getting. So what we have is we have phi s. So let's calculate phi s. It is in electron volts. I'm writing Q for now. What is the value? So we have 4 electron volt as the this is 4. This is Eg by 2. So it is, I guess, 1.5 by 2 plus EI minus EF is nothing but VTL and NA by NI. So you need to calculate it. So phi s will be some volts. So this is 0.75 plus 0.026 ln. I've given 1 as 12 and 1 as 18, so 10 raised plus 6, 4.75 plus this thing. Has anyone calculated this? Okay, so let me do it. It is coming out 0.359. If there is any calculation mistake, please let me know there only. So this is 5.109 electron volt. So 5 ms is coming out to be 5 ms what? It is given 5. 5 minus 5.109, it is minus 0.109 electron volt. Now we have this 5 ms. We need to calculate Cox and we need to calculate QSS is given. So Cox is the second part, which is epsilon ox by Tox. Epsilon ox is nothing but 25, 8.85 10 to the minus 14 by Tox is what is I have given. Tox is 100 angstrom. Okay, is my screen visible? Okay, I guess.
No,
No,
sir.
sir. No, sir.
Okay, okay, yeah. Let me check. Give me a moment. Is it visible now? Am I audible?
No, sir. Not visible.
Yes, sir.
Ye- yes or no?
I
Yes,
can
sir.
see it.
Yes, sir.
Okay, okay, yeah, fine. So Tox I have given as 100 angstrom, so that will be, I'm writing in centimeters, so that will be minus 8. So Cox will be, again we need to calculate this, is 2.2. Okay, so it will come out to be 2.2125 minus 6 farad per centimeter square. So now we have everything. So I'm calculating VFB, which is 5 ms and SQSS by Cox. 5 ms was 0.109 as the trap charges are 5 10 is per 10 into Q. So these are the trap charges, and this is Cox, which is 2.2125. Yeah, so this will be VFB. So this is minus 9, this is minus 3, this is 8 by 2, so it will something point 4 something. So has anyone calculated VFB till now? Mm, so what I'm getting is 0.1126 volts. You can confirm. I'm not sure about the calculations, but this is what I've got. So the second part that we need to do is a depletion region. So by depletion region, I am referring to the maximum depletion width. So this is now the direct case. For the formula is under root 4 epsilon s phi f by qna. So we have everything. Maybe you can give the answer quickly. And I hope you have the clarity that for the depletion region, we will use the epsilon for silicon. And for the oxide part that we were doing earlier, we were for the Cox, we were calculating or using the epsilon relative of the HFO2 that we have. So in this, the epsilon relative will be 10, that is given in the question. Is this clear? The thing that I have just said?
Yes, sir.
Yeah. So just quickly let me know what is XD that you are getting.
Sir, can you show us the question once again?
Yeah, sure. Is there any problem that you are getting in solving? It should not take this much time. Okay, so we have everything. Uh, we have 10 liter is 40. Pi FP calculated 0.329. Q is this and is this. So any answer? It's 30, 30 minus. So we have this and this will get cancelled. It's a 32, 34, 0.3, around 10, 10 by paired is around. So I'm getting 2.82. This is minus 7 if I write 28.2 nanometer. Uh, is there any answer that you have got? Do you don't you have calculators with you, like for a quick solution? Please, from further classes, do keep a calculator with you if you don't have right now, because most of the problems are numerical from now on, so that will be better. The third part is the threshold voltage, which is nothing but VFB plus Q depletion by C of plus 2 phi F. Do you want to calculate it or I should go for it? Please let me know.
We will do, sir.
Okay, so try to do it a bit quicker. So we already have VFB, we already have this. We just need to find Q depletion quickly, which is nothing but QNAXD. So we have just calculated XD, NA we have, Q we have. So it should not take 2-3 minutes, like more than 2-3 minutes. So let me know what you are getting quickly, everyone. Any answer? So let's start with Q depletion. Has anyone got the value of Q depletion? Stays.
45.12 into 10 to the power of 8.
It should be -8, I guess. Uh, XD was 2.82 -6. So I've got 4.512 as per -7, or 45.12 times per -8. And okay, I've got one answer, I guess, in the chat box. It is 4.5 nano coulomb. Okay, so it should be 4. What have you written? 4.5, not nano, but it is 10 is per -7. I hope nano is -9. Okay, so we have the Q depletion. So it was, I'm writing the VT now. So VFB is 0.1126. Q depletion is 4.512 times by -7. COX we calculated, I guess, somewhere. COX is this 2.2125 times by -6. 2.2125 times by -6 plus 2 into 0.329. Sorry. is 0.359, right? So this is simple, I guess. So this is minus 0.1126 plus this will be minus 1. So it will be how much? It is almost twice. So twice means 2 to the will be 0.204.
0.020.
Sorry,
That only, sir. 0.20.
yeah. So 8, 11, 7. So this will give a VT of zero point 0.9 is there, minus zero point 0.1, something around 0.80 is something will come. I don't know. 809 volts. So what I'm trying to say now is this is a CV plot that you have all read till now. Sorry. So at flat band the depletion starts. So this is nothing but 0.0. Sorry, not 0.0. 0.11 minus 0.1126. This is a VT which is 0.809 volts. This is Cox which is 2.2 something. It's for minus 6, I guess. What was it? Yeah. And this is again Cox. And this is a C minimum that you can calculate using epsilon Si by XD. Does it make sense? Everyone? Do you understand this question? Any doubts?
No, sir.
Okay. So maybe before going to further question, let me clear one more concept, which is the CV part for the low and high frequency, and then we'll quickly move to the assignment problems. So CV measurements is one more important topic for this particular lecture. So we have already seen that uh, how a CV plot comes, like how it goes down and how it goes up because of the series of depletion and the oxide capacitance. So in general, what we do, how do we capture the CV? So I hope you know that capacitor does not work with a DC voltage. Capacitor blocks the DC voltage and it only works whenever we have the application of the AC voltage. I hope you already know this. So let's say we have this oxide, we have this metal, and we have this as ground, let's say. So in general, to do the experimental analysis, what we do is we apply this VG, and with this we apply a certain AC voltage, which is, let's say, maybe I can denote this as amplitude. Let's say it is Vg and this is sine 2 pi ft. And this f is nothing but the low and high thing now. So low and high frequency will be judged by this particular frequency because the capacitor cannot uh, be measured only with the DC frequency. So let's say, sorry, with the DC voltage. So let's say this is with respect to time and this is the voltage. So what we do is at this voltage we apply a certain AC signal on top of this. So this is Vg and this small voltage change is nothing but small Vg times sine 2 pi ft. I hope this is already covered in the theoretical lectures also. I'm just covering it again. And the capacitance is nothing but the dq by dv, the change in charge with respect to the voltage. So if I talk in terms of the simple capacitor, that is we have a metal, we have an insulator, and then we again have a metal, and we do the same thing to this. Sorry. Yeah. We apply a certain DC plus a certain AC. So what will happen? The CV curve, how it will look? Someone quickly tell. Any guesses?
For low frequency, it will be the same U-shaped curve.
No. I am asking about a metal, then an insulator, and then a metal. A simple capacitor, not a MOSFET.
It will be constant.
Yeah. So this will be a constant which is nothing but epsilon ox by T ox. So that is good. So now once we talk about the MOS capacitor, as we have already did. So let's say the case one Again, if the Vg is less than Vfv, there will be accumulation. The plot will look till accumulation, it should look constant. Let's say this is the y-axis. I know, I guess we all know that it will look ultimately like this. So till accumulation, it will be Cox because of the accumulation of holes only. And again, the frequency is low. Even if it is high, it will not get affected. Why? Because I'll let you know later. For case 2, we know that when the Vg is less than the threshold voltage but greater than the flat band, what we have is we have a additional depletion region here. I mean, let's say this is insulator. We have a depletion region which is xt. So we have in total the oxide capacitance as well as the depletion capacitance. So we have a decrease in this capacitance. So this, maybe I can denote it with this red. It will start to decrease. The red line is showing the depletion region. Sorry. Yeah. And then if we go to the case 3, which is when Vg is greater than that of Vt. So what happens at Vg greater than that of Vt is we have an inversion and we have a capacitor created again. Let's say this is the metal, this is the SiO2. So this is positive, positive, and we have accumulation of electrons at the surface, and the capacitor again goes back to it starts to increase and it goes back to the oxide capacitor. So this is what happen in general for any MOS cap. So what we have not considered till now is the frequency effect. What can the frequency do? So let me put the heading low and high frequency. CV characteristics. So first of all, what is low frequency and what is high frequency? So by low frequency, what we mean in general is we are sweeping the DC voltage very slowly, and the AC signal that we have applied on top of the DC is also very low, which I maybe, yeah, this is the thing. So we are sweeping the DC voltage slowly, and also the AC signal that we have applied on top of the DC pulse is also having a very low value. So this is what we have, a low frequency. So what happens is because it, maybe I can first draw and then explain. So accumulation, then we have depletion, and at last we have inversion. So what happens for accumulation and depletion? So basically accumulation, and why accumulation happens is once we apply a negative voltage, let's say a negative voltage, I'm writing minus minus, and we have this SiO2. So accumulation happens because of the holes, and holes are what? The majority carriers. So the time that is required for the majority carriers to what to say to come at the surface is very less as compared to the minority carriers. I hope you do remember the time things, like the diffusion length is nothing but, sorry, I hope you do remember these concepts. D and tau and something like that the formula was. So the main objective of telling this is the majority carriers that we have can quickly come at the surface, but the minority carriers might take time to come at the surface or to even make a layer at a complete layer at the surface. Does it make sense, the thing that I'm saying right now? First of all, they are minority and they are less, and they will take more time to come at the surface as compared to the majority. Does it make sense?
Yes, sir.
Yeah. So if it makes sense that even if we apply a very high frequency in which these carriers don't have such time to come at the surface, so the accumulation and depletion region will remain same even for a low or even for a high frequency. Why? Because we are caring about the majority carriers. The curve will only change because of frequency in the inversion region. In the inversion region, because the minority carriers are the responsible for the characteristics in the inversion region. Does it make sense?
Yes, sir.
Yeah. So in inversion, what happens? So basically, so let's say depletion has happened. This is a depletion width, and we have applied a very high frequency such that these depletion carriers are there. Let's say Na minus are there, but the frequency does not have enough time to make this particular layer additional particular layer. So what will happen? This particular capacitance will think that it is still in depletion, and at high frequency it just stuck at this particular depletion capacitance. So this is the plot for high frequency, and this green one is for low frequency, which is the internal plot. And the plot changes only for the inversion region. I hope you know the reason now why it is only changing for the inversion region. And basically these electrons are generating because of the thermal generation. So we are comparing the frequency to the generation rate of electrons which are generating thermally. We don't have any source of electrons that we are giving till now. Does it make sense? The low and high frequency?
Sir, if the electrons are thermally generated, would that mean that XD would reduce the depletion length, depletion layer?
XT would reduce, you are saying?
Yeah, XD was exposed because of the electrons coming. So if now,
The depletion is region layer is because of the Na minus, the acceptor ions, not the moving ions. These electrons are the minority carriers, and these are the acceptor ions. So they are not moving anywhere. There is a
yes,
difference
sir,
between, yeah.
they were exposed because of some electrons occupying some hole spaces, right?
Yes, 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 exactly.
So now when electrons are generated
Yes.
because of thermal generation,
Hmm.
would that still go back, revert back to
Yeah,
non-ionized state,
yeah. So
thus
it,
losing the depletion layer?
yes, yes. So that is what is happening now. If when we are going from depletion to inversion, we are losing this, and that is why this capacitance is increasing, right?
Okay, yes, sir.
Yeah. So even let's say if I have applied a very high frequency, and do you know about MOSFET? Like the classes have been done for MOSFET.
No, sir, I haven't watched the videos.
Okay, so in MOSFET, what we have is, let's say, let me give you some idea. In MOSFET, we have the same structure, except that we have some source and drain, what to say, source and drain carriers, which are Na plus, which are very highly doped with electrons. So since we have this Na plus, these electrons can quickly make this inversion layer. So even if I give a very high frequency, this will always go up for a MOSFET as compared to a MOSFET. And in every VLSI interview, they ask this question that why does it happen? So if you know this, it is a good thing. Do you try, like, are you able to understand what I'm trying to say?
Not fully, sir.
Yeah, once you will go for MOSFET, so MOSFET is nothing but the MOS capacitor with additional, what to say, additional buckets of electrons. So this
Okay,
is what they call as source, this is what they call as drain, and this is what they call as gate. So till now, what we are dependent upon this minority carriers of electrons to get to form the inversion layer. And I'm saying that if we apply a very high frequency, these minority carriers will not be able to form the inversion layer, and that is why the capacitor will think that it is still in depletion, and the capacitance will not increase further or again. But if I have these buckets, these electrons will readily go into the channel, and this will go again up. Even it is not dependent upon the frequency now. So this is the beauty of a MOSFET. Right now we are
okay,
only
sir.
covering the MOS cap, so just forget about these two buckets. Where is that? Yeah. So right now we are dependent upon the frequency. So if we have a very high frequency, we will not be able to form this, the thing that I am removing right now. Okay. I hope it makes sense now.
Yes, sir. So at high frequency, the thermal generation of electrons will take place, but it
Yeah, it is
won't
not.
compensate for
Yeah,
the
yeah. It is not
charges.
fast enough basically to respond to the high frequency variations.
Okay.
Yeah. And similarly, there is one more case, I guess you only asked in the last lecture, which is known as the deep depletion region. So the deep depletion region means the, in fact, like I have made you saw here two things. One is the DC sweep and one is the frequency. So for the deep depletion, what we do is we increase the DC sweep also very quickly, and we also increase the AC frequency quite quickly. So what MOSFET thinks is that the depletion region is uh, still increasing, and is increasing because of more and more Na. So what happens for a deep depletion? Some other color. So even after depletion, this starts to decrease. I mean, it will not go to negative. Let me make it again. So in deep depletion, this will be the plot. So in deep depletion, I'll say again, the DC voltage sweep rate is also very high, and the high frequency is also there. So now the DC sweep rate is so fast that the inversion layer itself does not form fast enough. And if it is not forming, that it is thinking that we are still increasing the depletion region, it will go like this. The capacitance will be decreasing more and more if the depletion region is getting increased. So this is basically everything about the CV measurements of a MOS capacitor. Does it make sense to everyone?
So what do we mean by the DC sweep being very fast? Does it mean that the DC value is oscillating between some values
No, no, no.
very
Okay.
fastly?
So see, like practically when we apply a voltage, let's say I have maybe, let's say I have a motor, a small motor in which we are applying a cell, right? So that cell has some 5-volt battery. So basically it starts from 0 and go to 5 volt in some time. Like in practice or in reality, we do not see how this voltage is going from 0 to 5 in a second. So this, by meaning of DC sweep very fast, is we go from 0 to 5 very quickly. Like let's say this particular line is 0 in this particular plot. Okay, give me a moment. So this particular line is 0 and this particular line is VG. So it will take some time from to go from 0 to VG. Like in general or in reality, we do not see this. Like if we say I have applied a 5 volt, we thought that this 5 volt is already there, but we it is there is some time from which it takes to go from 0 to VG also. So that DC sweep I'm saying is very fast. So it will go to VG in an instant, and then this AC frequency is also quite high. By frequencies high, I mean this, and the pulse will be very what to say, the bits will be very less. Make sense?
Yes, sir. Then in that case, once the DC sweep has gone very fastly,
Hmm.
like a pulse,
Hmm.
finally it will remain at that high value, right?
Yes,
Then in
yes.
that case, the electron should be formed, right?
uh, I know frequency, I'm talking about this AC signal frequency. So if the frequency is fast, then the thermal generation will not be that fast enough. The DC sweep, don't compare it with the
Okay.
DC sweep. मतलब focus on the AC sweep for this particular plot. Like these plot focus on the AC sweep, all the things that I'm telling for the low frequency and high frequency. In the deep depletion, what I'm saying is both the things are high, and in practical we see that there is an increase in the depletion region uh, for some indefinite period. So that is why this capacitance will like follow this particular thing. Like it will go on decreasing basically.
Okay, sir.
Yeah. So I hope this is all clear. And so can anyone tell, if I make it for a PMOS, what will change? How will it look like if I make it for a PMOS? Anyone wants to maybe try? No guesses is very easy. It will just invert with respect to the y-axis, right? PMOS is negative voltage. So accumulation will come on the right side and the depletion and the inversion will come on the left side. Does it make sense?
Yes, sir. VT would be negative voltage.
Yeah. Yeah, by VT I remember this. I was sorry, I forgot to label this. So this particular voltage is a flat band voltage. This particular voltage is a threshold voltage. This particular capacitance is the oxide. Sorry. Yeah, where was I? This is VFB, this is VT, this is Cox, and this is C minimum. So these are the things that you will be asked in general to calculate in the numericals. Let's maybe move ahead to the numericals now. Try to do it quickly and let me know the answers also. So we have the first question. It says a student has a MOS cap which he has taken from market to characterize them. The basic structure of MOSFETs is MOS cap is given below. A VG voltage is applied DC voltage and VS is a small signal AC voltage and with the frequency omega. The CV characteristics of one of the MOSFET taken at two different frequencies is given here. Based on the given data, the first question is the substrate doping and the type of MOSFET is. So quickly let me know what is this.
P-type and NMOS.
Yeah. So it will be a P type and an NMOS because we have the change in frequency at the right side. So this will be happen for a P type substrate and it will be a NMOS. So let's cut this N type. So the second question in continuation is if the area of the MOS cap is 3 into 10 raised to the power minus 3 centimeter square and the thickness of the oxide layer is sorry, it is asking for the thickness of the oxide layer. So can anyone tell how to calculate this? Yes.
Oxide capacitance is given, so epsilon naught A by Tox.
Where is the oxide capacitance given?
From the graph, 120 picofarad.
Yes, that's correct. So maybe I can solve this. It is nothing but epsilon ox by Tox. So now the question is asking the capacitance, oxide thickness in micrometer. And I hope you know that this oxide capacitance that we always calculate is farad per centimeter square, right? So that is why this is into area. That is why they have given the area to calculate the exact Tox. Is it fine? Basically, if I'm multiplying this by area, so this will be in picofarad or farad, whatever it is. Otherwise, what we write in general, it is picofarad per centimeter square. Make sense?
Yes, sir. So in the graph, we are given with the total capacitance.
Yeah, it is not per unit area, it is the capacitance. In graph,
Oh,
it is always the capacitance, not in per unit area. So yeah, so that is it. So this is 120 picofarad. Pico is minus 12. Epsilon ox, I guess they have the given 3.9. Here is epsilon ox and sorry. Why have I used 3.9 and not 11.9? Can anyone tell?
the 9.9 would be for the depletion capacitance.
Yes, that is good. So epsilon ox by T ox I need to calculate and the area is 3 10 minus 3. So quickly let me know what is a T ox. Sorry. Okay, still my screen is shared. You can see my screen, right?
Yes, sir.
Yes. So what is the T ox that you are getting? This is very easy now. Don't take more than 1 minute. What I can see is 120 minus 2 minus 2 minus 5 minus 5. This is 824. 236 something. Okay, so I've already got one answer 0.086. Okay, so answer it should be in micrometer, right? The answer that you have got. Yeah, only one. So I'm assuming this calculation is correct. It will come out something around this only. 8 will come. I am sure about that. So I guess we can proceed. Yeah, that is great. I've got the confirmation. So now the further question is invoking the delta depletion approximation. I hope you know what is depletion approximation, right? Can anyone tell what is depletion approximation? Anyone? Any idea? Okay, so the depletion approximation basically states that the depletion region that is created in the depletion region of the MOS cap is basically depleted of any mobile carriers. So that is what we call as depletion region, because ideally it is very difficult. So let's say this is SiO2 and this is a depletion region. So the depletion approximation states that it is only containing the acceptor ions. It is depleted of any mobile carriers, so that we can treat it like a depletion capacitance. So that is what we call as the depletion approximation. So in this particular question, we need to calculate the depletion width. Oh, sorry, the maximum depletion width. So this is again a straight away question. It is even given that when phi s is 2 phi f, you need to calculate. So shall I calculate or you want to calculate it quickly? I'll also do it side by side. So depletion is epsilon Si by xd into what is area. Area is given, right? Yeah. So do we need to find this xd? We have this C depletion. So can anyone tell what will be the C depletion? This is good now. Let me check your concepts now. So what will be the C depletion? Can anyone tell? Think about it and then tell. Am I audible? Uh, I hope I'm audible, right?
So
Yes,
the
sir.
40 picofarad value,
40
uh,
pico.
that is
Sorry.
actually the parallel combination of
Yeah,
set
yeah.
capacitance and depletion capacitance.
Yes, yes. That is good. So what will be the depletion capacitance then? So maybe you're trying to say that 1 upon C equivalent is 1 upon C oxide plus 1 upon C depletion, right?
Yes, sir.
So C equivalent is 40, you are saying,
Yes,
and C oxide is 120.
120.
C depletion you can calculate. That is good, yeah. If if you are able to get this, then it is very good. So C depletion will be 120 times 40 upon 120 plus 40. So it will be 164. Sorry, say 4 4 sorry, it will not be plus. I have given 120 minus 1 by 40 minus 1 by 120, 120, and this is 2. So C depletion is coming out to be 60 picofarad. If I'm not 60 times 10 is 1 minus eco is minus 12. SI is now 11.9, 8.85, 10 is minus 14 into area. Area is what? Area was given something, 3 times 5 minus 3. So quickly let me know the answer. Maybe I can calculate it quickly. 10.9 multiplied by 40.4 divided by 60 into 3. So I'm getting 0.526 micrometer, which is option B. Is it fine?
Yes, sir.
Yeah. One thing I'm impressed by the students that they were able to get this depletion capacitance. So let's move ahead. So in the above experiments, the student finds out that two sets of CV curves as shown in figure. The gate area is same, so area is same. They are saying choose the correct option where Na1 and Na2 are the doping concentrations. So yeah, Na1 is greater or lesser or equal. Can anyone tell? This is again a very good question. Anyone wants to give it a guess? Okay, so can you tell why A? Uh, are you saying
So
something?
capacitance is dependent on depletion width,
Capacitance is dependent upon depletion width. Okay, let's say right place.
inversely dependent,
Yes.
and depletion width is in turn inversely dependent upon Na.
Okay. So if you have a higher Na, we have a smaller depletion width. A smaller depletion width means higher capacitance. You're saying.
Yes.
Okay. Yeah. So that is one way of answering this. This is correct. So basically, we will have a higher C minimum if we have a higher Na. We have a smaller depletion width, and that was resulting into a higher C minimum. So the answer will be correct. And one more thing that we can judge on the basis of is the threshold voltage. So if Na is higher, then the phi f will be higher, right? And we will require more Vt, right? So the Vt for one is higher as compared to the Vt for second. So this is both the ways of getting or answering this. Na1 is greater than that of Na2. Is it fine with everyone? I hope it is. So let's move ahead. Okay, so this is a straightforward question. Please let me know. What are you thinking? Now you will be able to answer these questions in seconds if you are able to grasp all of this. Any guesses for this?
Both are true.
Yes. So the low frequency and high frequency curves are identical in accumulation. Why? Because the majority carriers are there involved, and the accumulation and depletion are characterized by okay, yeah. So oh yeah. So it is also an explanation of S1. It is also given. So they are characterized by majority carrier response time, which is much smaller than that the applied frequency. So they can quickly respond basically even if you apply a very high frequency. So both are true and it has a correct explanation. So moving ahead. So we have a MOS capacitor which is fabricated on a p-type silicon. So p-type silicon means it is a NMOS where the metal work function is, so phi m is 4.1. Then we have the electron affinity of silicon which is 4. You can also do it side by side. I'm also doing it. EC minus EF is zero point 0.9. And what is this? If the major flat band is also given as minus 1 volts. What is the magnitude of fixed charge? So basically we are trying to calculate the what we are trying to calculate is the trapped charges that are there. So we know that this is a relation VFB is phi ms minus the fixed charge by Cox. So we have VFB, we have phi m, phi s we can calculate by using these two things, and QSS we need to calculate Cox. For Cox we require the oxide thickness. Do we have that? Where is oxide thickness? Okay, so I guess the oxide thickness is not given. How can we calculate then? Oh, yeah, yeah, it is given here. Yeah, yeah, everything is given. So let's calculate. So phi s is electron affinity plus EC minus EF. It is directly given, so it is 0.9, 4.9. So Vf is minus 1. It is 5 ms, which will be 4 minus 4.9, that is minus 0.9 minus QSS by Cox. Cox is, let's try to calculate. Cox is epsilon ox by Tox. So it is 3.9 into 8.85 minus 14 by Tox is zero point 0.1 micrometer. So this is minus 5. This is 3 into 8 is around 3.4515, 10 is from minus 8 farad per centimeter square, which is I'm writing here. It's from minus 8. So I guess I've done it correctly. 5 ms. Oh, sorry. It is 4.1 minus 4.9. So it is 0.8. So it is minus 0.2 times. So QSS is nothing but 0.2 times of Cox, which is this. It is Coulomb per centimeter square. And what we need to do, we need to calculate in nano Coulomb. So it is minus 9 will come. So it is 2 into 3. So it is something 6 point something nano Coulomb per centimeter square. Is there any option like that? Yeah. A will be the answer. 6.9 it is saying. Yeah. Is there any doubt in this? Anyone any doubts?
No, sir.
Okay. So let's move ahead. This is again a good question. So it is asking that for a MOS cap, VFB and VT are the flat band and the threshold voltages respectively. So if we, the variation in the depletion width for a varying gate voltage. So if we increase a gate voltage from, let's say, negative to positive or to even greater than VT, how the depletion width variation will come. So can anyone tell what will be the answer? This is a very good question. So let's go one by one. So in accumulation, what will be the case? Will there be any depletion layer?
No.
Yeah. So then if we go from greater than flat band, the depletion will start to happen. So the depletion layer will increase or decrease.
Increases
Yeah. So it will increase till when?
till the threshold voltage.
Yeah. So it will increase till the threshold voltage, and after that, what will happen?
It will remain constant
Yeah.
because then the electrons will take over.
So what will be the answer then?
Minority case. A would be A or B could be an answer.
One is the answer. So A or B.
B is the answer
Why? Like why
because
not
in
A?
A,
Hmm.
it becomes constant right from
Yes.
0, Vg equal to
Yes,
0.
exactly. So till VT, it will increase the depletion layer, and then it will remain constant. So that is a very good observation again. So option B will be the correct answer. I hope it is clear to everyone. Shall we move ahead? Okay. So in a MOS capacitor, the capacitance at the threshold voltage is due to what? Any guesses? A, B, C, D, E, F. Let's say there are 5, 6 options.
C.
Yes. So at threshold voltage, what we have? We have the series combination of the depletion and the oxide capacitance. Is it fine? Shall we move ahead, everyone?
So why couldn't it be in parallel?
Why? Why they should be in parallel? I mean, you can see now there is a direct two capacitances, like physically I'm saying that they are connected physically together, so they should be in series, right? In parallel we need to have a capacitance like physically here. Let's say this is some voltage and this is ground, and in parallel what we have in common is the voltage, so we need to have one capacitance here. For now what we have is we have one capacitance here and we have some capacitance here, like they are physically joined. So this v1 will be less than this v2, but it is, the connection is like this, right?
Yes, sir. Voltage is getting divided between
Yeah,
both.
yeah, exactly.
Okay, sir. Got it.
Yeah. So I guess these are some of the problem for this assignment that you have been given. So what will be the answer? Please let me know. This is very quick now. Any guesses?
One is false and two is true.
Okay, so let me see. So capacitance for a MOS capacitor in strong inversion. So basically, so this is larger when measured at high frequency. So we know that at high frequency we have a smaller capacitance. So yeah, one is false. At low frequency there is enough time. Yeah. So this is what we already covered. So one is false and second is true. Is there any option like that? Yeah. Option B is the correct answer. So let's move ahead quickly now. I hope you all are able to understand this. Okay. So do you know the concept about effective oxide thickness EOT? Have you heard about it? Can anyone tell if they have heard?
No, sir.
Okay, so I guess this is the topic for MOSFET. So maybe I'll cover it more thoroughly in the next lecture, that is for the MOSFET next week. So maybe we can skip this question and I'll cover this question in the next lecture. That will be basically for MOSFETs. I hope it is fine. So let's move ahead. Yeah. So we have an ideal MOS capacitor with a 10 nanometer gate oxide. So let me give you quick ideas how to solve these questions because I cannot give you the solution directly. So we have 10 nanometer gate oxide means we have the TOX given, we have the Na given, include the effect of flat band voltage. So flat band voltage is nothing but pi ms minus the fixed charges by Cox. Fixed charges are also given, and I guess we have done this question in the initial part if I'm not wrong. With the same values or not, I'm not sure. So we can calculate VFB, everything is given. And what else? Tox is given, so maximum depletion width we can calculate, and minimum capacitance is nothing but C minimum will be epsilon Si by W max. Is it fine? I'm not solving it. Maybe you can take a screenshot and let me know the answer in the next lecture. I guess this is this year's assignment only, so you can. It is just solution now if you know the concept now. Is it fine? Shall we move ahead?
Yes, sir.
Okay. So again, a similar question. This year's assignment. So what we have, a gate oxide thickness is O. So it is asking for TOX. I hope it is now very clear. How do we calculate it? Anyone? Any guesses?
Epsilon SI into A by C max.
Si or oxide?
Oxide, oxide.
Okay.
Oxide.
By Cox. And Cox is what?
7 picofarad.
7 feet apart.
Any other thing in this formula?
A.
Yeah, area, because it is picofarad. So I guess you can calculate this again. You will get the answer. Everything is given. So let's move ahead. Yeah. So this is the final question. So let's say we have a two MOSFET with different oxide thickness TOX. One is having TOX 50. One is having 150. So the question I'm asking that if we increase the oxide thickness, so CV will shift up, left, right, down, no change. So if we increase TOX, what will happen to COX? Anyone? This is very straightforward, I guess.
Both are inversely proportional, so it will move upward direction.
No, if
Decreases.
yeah, it will
It's down.
decrease. So it will go down, right? Not upward. I hope it is clear. We have increased the TOX. It is saying that it is increased. So Cox will decrease, so the CV characteristics will shift downwards. Is it fine?
Yes, sir.
And if the oxide thickness is decreased, the VT will shift. So Tox will decrease, then VT will shift, the threshold voltage basically. Any guesses? Okay, so let me give you VT. We have just calculated. I hope you remember. It is VFB plus Q depletion by Cox plus 2 pi F. Now can anyone tell?
Moves to the left.
Left. Okay. So if Tox will decrease, Cox will.
Increase.
Increase.
If Cox will increase, this term will.
Decrease.
Decrease.
So VT will.
Decrease.
Decrease.
Yeah. So it will move to the left. I hope it is clear. Is it clear to everyone?
Yes, sir.
Okay. So I guess that is it for this particular week's question. And maybe I was thinking I'll take one extra lecture, maybe after taking all the 12 lectures, or like I wanted to give some of the shortcut formulas to calculate all these. Like I have some set of formulas that you can directly calculate using those formulas. You just need to put some of the values that are given in the question. So maybe that I'll take after taking all the 12 lectures for this particular course. So we'll see it later. So in the next lecture now, in the next week, we'll be covering for the MOSFET, which is again a very important topic. And I'll be covering some of the concepts initially. And the MOSFET will be now talking about the currents, not the charges or capacitances. So please do join the next lecture, which will be again next week, same time. So is there any doubt, or we can dismiss for today? Any doubts?
No, sir.
Okay then. So thank you for joining. We can meet next week at the same time now.
Thank you, sir.
Yeah, welcome.
Thank you, sir.
Yeah, welcome.